Good morning. Okay, so good morning, everyone. So basically, in the last lecture, we were discussing about the reliability concern. We started discussing about the reliability, where we talked about the time zero variabilities and time dependent variabilities, which we called it the temporal degradations. And we understood like how this MBTI, SCI, TDDB, and the process variation works. What is their impact, and with the skill technology or with the lower technology, how they are going to impact the performances of your circuits and the systems. Other than these things, we all yesterday we started discussing about there is one more reliability concern that we can call it the soft error or radiation hardening. So radiation hardening, why radiation hardening is important? Basically, if you are utilizing your chip or your circuit for the harsh environments like space applications or in nuclear environments where the probability of high energy particles are very high, in this case, you need to make your circuit robust against those high energy particles. So this kind of phenomena, like say, effect of radiation can happen either in combinational circuit or in sequential circuit. In both, it is possible. But in combinational circuit, it generates some glitch, and again, it can recover back. But if the glitch is generating in the sequential circuit like a memory, in that case, that glitch can flip your logic and might be you will lose your information. So this kind of seriousness we have in terms of the radiation hardening one. So we'll try to discuss like what the soft error mechanism is, how it impacts the circuit, how we can model a soft error pattern or glitch, and how we test or how we evaluate any circuit using any software tool like Cadence. So basically what happens if any high energy particle strikes on any devices, it generates secondary electron hole pair, okay? And because of that, they generate and they are collected at most sensitive node in the devices like a drain, where they generate a small glitch. And if this glitch is crossing the threshold voltage of that logic, let us assume, let me tell you a simple example. We know that I have an inverter, and in inverter characteristics, there is some trip point voltage, okay? So if it will cross the trip point voltage, might be it can be considered as a logic 0, and if it is below trip point voltage, it can be considered as a logic 1 and logic 0, okay? So if the amplitude of that glitch is crossing that threshold, which we are deciding like a trip point voltage, it means that you will get a different kind of logic, okay? So ultimately, they are being collected and they can generate a glitch at the sensitive node. And there are many sources which are responsible to create the secondary electron hole pair, or because of their strike, it could be neutron, proton, alpha particles, or many things. They have different energy and they can be found at different level in the terrestrial environments. Okay, and I think if you want to explore that one, Aryan has published a good paper on review paper on that. You can go through it. You can find all these relations where you can find what kind of particles. So what you have to take care of, that is already discussed very well. So this is what happens. If you talk about like how it happens, so to test or at the simulation level, how you can do that. Similarly, I'm simply considering a simple inverter circuit. So what I will do, I will inject a current pulse of having some equation, double exponential current equation is there. Let me open that equation as well. Okay, yeah, here it is. So what you will do, let us assume if I have an inverter, if the input of that inverter is logic 0, and what I'm expecting that my output should be 1. So this is actual 1. But because of that glitch, your output can move to 0 from 1. And for that, you need to take out the current from there so that you can change the logic. Okay, so you have to apply a current of reverse direction or opposite direction. Similarly, if you want to change the logic at the simulation level, like if you have input 1, you are expecting your output should be 0. In that case, you want to, if in this case, if you want to flip your logic from 0 to 1, then you have to push some more current. So ultimately, we are changing the current because of that glitch, and that is modeled by the double exponential current, and this is doable. The similar thing can be applied for sequential circuits as well. not only the combination, it can be applied to the sequential. We have to apply that current at the sensitive nodes, like storage node in the memory. If you talk about 60, we have two storage nodes, so you can apply at either Q or QB, and accordingly you have to see like how much amplitude I need to flip the logic at another node, because ultimately the SRAM is made of like there is a latch, and ultimately we need two inverters to create the latch. Okay, so and if some glitch is generating, might be it can cross the threshold trip point voltage, and might be other node voltage can change its status from 0 to 1 or 1 to 0, whatever it has before. So this is what the software mechanism and how it works. Let us try to understand the importance of this glitch in a circuit where we have all the combinational as well as the sequential modules. Okay, so let us assume I have this NAND gate. Okay, and both the input of both the NAND gates we have connected to 1. So ultimately, what I'm expecting the logic should be 0 here. Okay, if both are 1 1, then it means the output will be 0. Now let us assume at this node one particle is like high energy particle strikes and it generates some glitch. Okay, how it generates I have already told you in the previous slide. Let us assume at this node one glitch is generated. Ideally what I should get, like, because both the input of both the NAND gate is 1 1, here I should get 1 0, and accordingly inverter will pass and then it should be 1. Ideally it should be 1, but because of high energy particle strike at this node, it has generated a spike, and that spike can be considered as a pulse for the input of this inverter. And if it can be considered as an impulse for that inverter, it will disguise that impulse, and might be from high it can generate a spike or generate a pulse like a low logic. Now the actual one I was expecting like it should be logic 1 always, but because of that impulse, because of that spike, it has created a pulse, and that can be at logic 0. Okay, now if it is the case, then I will tell you why I have used NAND gate over here. Let us directly come to this point. I will tell you what is happening over here later on, don't worry. So let us assume, leave these two things. I will tell you later on what is the importance of these two. Let us assume I have this inverter, and again I have passed through one more inverter. So what I will get? I will get a pulse something like this one. This will be a complemented version of this pulse. Okay. Now, in reality, I was expecting, let us assume here is logic 1. After passing through inverter, it should be 0. It should be, logic 0. Here is I'm expecting logic 1. And again, if I'm passing it through one more inverter, logic will be 0. So the 0 is initially connected to this D. Okay. So whatever output I will get, let us assume I have initiated this clock. Okay. So the output of this D flip-flop will be the logic 0 only if I don't have any spike. But what is going to happen? Let us assume some particle strike at this sensitive node. In this case, after passing through two inverters, forget about this NAND gate 1 and inverter 2. I will tell you what is the importance of that one again. Okay. So let us assume I have only inverter 1, inverter 3. In this case, I will get one impulse here. So the D flip-flop output will be like logic 1 instead of logic 0, and that can change the status of your sequential circuit. So this kind of problem, and might be it can. So the logic was like initially I was expecting it should be logic 0, but now the D flip-flop will store logic 1, which is completely opposite whatever I was expecting. Okay, so this kind of problem can impact the storage element, and that can you can lose your data because of this high energy particle. Now let us come to the point why I have considered this NAND 2 and inverter 2. We know the equation of NAND 2, how it happens. Let us assume what is we know that NAND gate is nothing but A dot B bar, right? So what is the truth table of this one? 0 0 0 1 1 0 1 0. What is the outcome? What is the output? 1 1 1 0. 1 1 1 0 means like if both are 0, then both are 1, then you will get 0. In other cases, you will get 1. So what you can do? Simply this NAND gate can be used to mask the thing. So let us assume if one of the input of this NAND gate is at logic 0, then what will happen? whatever the change I have in other input, it will not impact directly. I will get the logic 1 always. Is it? So what it means, even though you have some spike here, you are going to get always logic 1. So this is what we can call them the logically masking the things. You are masking the impulses. I am going to explain in more detail later on, don't worry. So this is what it can be done. So this can be controlled to mask the logic or mask the impulses, impact of those impulses, if you have received at any sensitive node in the circuit. And inverter is just to make this AND kind of logic, okay, so that I can get whatever I was expecting over here. I hope you understood what I'm saying here, okay. Now let us try to understand one more thing. Yeah, similarly, so this is the impact on the impulses, how this impulse generated, and accordingly how it can change the status of your D flip-flop. Now let us talk about this one. It can also create certain delay, okay. So yeah, before that, let me go to the next circuit and I will come back to this point again, okay. So please hold on. Let me go to this circuit, this waveform. Initially, what I was expecting, let us assume if I do not have any spike. If I don't have any spike, I was expecting the output of the first VO1 is something like this one. Initially, it was 0, and now it is changing from 0 to 1. So this is simply the output of an inverter, which is changing the state from 0 to 1 or 1 to 0, okay. But now, let us assume one particle strikes at this point, okay. If a particle strikes at this point, initially my output was changing from 0 to 1, but because of this particle strike, this will again fall down to 0, okay, and it will come to 0, and again it will maintain logic 0, and it will recover after a certain period of time, whatever the time period of your impulse is. So let us assume this was your time period of impulse. So for that time period, it will maintain logic 0, and again it will start making the same logic which I was expecting. So my expected output was this one, but I will get the same logic or same output after certain period of time or certain delay. So this is what I can get, certain delay in the output. Initially, if I don't have the impulse, I will get output at VO3, like what is the VO3, I will tell you. Okay, I should get the output like this one, but this output will be delayed because of this impulse. So it is not only, so what I just want to say, yeah, let me go back to the previous one then. Here. So yeah, VO1 and VO3. So what happens? I was expecting I should get my output at t is equal to 0 time, but because of this impulse, I am getting output after certain delay. So this is not only to change the status or change or flip the logic, it can also delay the circuit. So soft error is also responsible to delay the system, okay, because it is changing its status and again regaining its logic, and maybe it can delay your system. So these are the two impacts that we can think of. In sequential circuits, they may flip the logic, or they can, in combination logic, they can delay the system. Okay, so these are the two impacts. So this is what we don't need. Let us assume I have some range of this delay, and because of this strike, or what can happen, your waveform can be delayed by some amount, and might be it can be beyond your limit of the delay, whatever you have decided, or specification, delay specifications. Okay, so if you have some threshold, like if you have given sufficient margin, then it's fine, you can work, your system can work. But if you don't have a sufficient margin of that delay, then might be it can add more delay than you was expecting, and might be your system may fail. Okay, so these are the impact on your impact of this particle strike on delay as well as the logics. Okay. Yeah, I was talking about the masking. Let us see how it can be done. So there's always a solution for that. What is the solution? The problem which I just told you, like if somehow, because what is happening? I'm getting an impulse like a double exponential pattern, but that double exponential pattern has been converted into the digital form. And now that becomes a valid pulse. Okay, let me go back there, what I want to say. Here, if you see, here it was a double exponential kind of glitch. That was kind of analog signal, like with time varying signal. But after passing through the inverter, that becomes a real digital signal, real digital impulse. And now you cannot remove it. Okay, so that's the problem. So how to overcome, how to remove, how to mask those things? Let us try to understand those schemes. So to overcome these problems, we have some solutions like masking schemes. And the first masking scheme, we can call them the electrical masking. How we can do that? Let's try to see. Yeah, I think I have already explained. Yeah, maybe this diagram will be helpful. See here, if I have a NAND gate, if one of the input is connected to logic 1, so whatever the input I will be here, that will complement it and I will get something. But if I have connected one of the input to logic 0, whatever input I will get, I will always get output logic 1. So this impulse can be masked because this ACT pulse was generated because of that high energy particle strike. Okay, so if I want to mask this one at the output, definitely I have to add one of the NAND gate in between so that I can maintain it to logic 1. But see, it is not necessary that you have to add always an AND gate, NAND gate. Maybe somewhere you need logic 0. That is also possible, but it is always giving logic 1. So what is the solution for that? I am giving the research problem directly. Someone can work on this. What you can do, you can simply add one XOR gate, one NAND, one XOR, based on the logic what you need. Accordingly, you know that XOR can act as a buffer or as an inverter. So then, so that you can make it like whatever logic you need. Okay, so it's not, you will not get always logic 1. You can get logic 0 or logic 1 based on your input if you are trying to enable your XOR gate based on your data. So this work has not been published. You can do anyone can do that. So but write my name. Okay. Yes. Yes, not inverter. It is holding the same logic in this case, na? Yeah, it is inverter. Yeah, yeah. It is. Then how you will mask that? My objective is not to pass the logic or not to invert the logic. My objective is to mask it. How you will mask it? Mask means like if there is any impulse, I don't want that impulse. So how you will do that? So you have to keep one of the input of this NAND gate to the 0. That will be masked. That is fine. So when you want to mask it, if you want to stop your impulse, then you have to mask it, and for that you have to use that NAND gate. But if you don't want to stop that impulse, connect to logic 1. The same logic will be transferred. Don't worry. Okay. So yeah. So this is what we can call them the logical masking. Electrical masking is something like this is really very difficult. Generally, this is possible with the analog circuits. How it happens? Let us assume you have generated some impulse, but pass through. So what I am expecting here in electrical masking, you must have a lot of like n number of stages, and each stage your amplitude should be attenuated. And if it is keep on attenuating, might be after certain stage, its amplitude is very minimal, and that cannot be considered as an impulse. But for that, you need large number of stages. This is not a good technique. Okay, so maybe some attenuator or something kind of things may be added that can attenuate these kind of impulses. Okay, so that's one of the solution or possibility that you can stop the those impulses flowing, like moving through the circuits. Third and very important thing is the timing masking. What this timing masking is? Let us assume I have a D flip-flop, okay, and let us assume this is the edge trigger, positive edge trigger. Okay, the symbol is not the positive edge trigger, but consider it is a positive. So, okay, initially consider it is a level trigger. Okay, if it is a level trigger, then what will happen? Let us assume this is a positive level trigger. So, whatever the positive signal if the clock signal is positive, then during the entire period of that positive clock pulse, if some impulse is coming, this will be transferred to the D flip-flop. But we know that the time period of your levels are more than the transitions. So if you want to avoid that, use the edge trigger instead of the level trigger. If you are using the edge trigger, this impulse will only be transferred when there is an edge or your spike is coming at this point of time. So this is one of the ways by which you can avoid it. Okay. So now because you have the positive level, negative level, positive is, negative is, but you have made your circuit in such a way like only it will be passed only in the negative is. So you have only very minimal chance like that impulse will be transferred. Okay, so by this way you can with the timing you can mask them. But yes, 100% masking may not be possible, because there is a possibility your the impulse is strike at the same time your when your age is either positive or negative. It depends what kind of logic you have used. So if it is coming at that point of time, definitely this solution is not going to be effective then. Okay, in that case you have to add the electrical masking. So yeah, these are some techniques. Like you can combine these two masking schemes, like is timing one, electrical one, logical one. Might be you can increase the probability of stopping those things. Okay, fine. Okay, so yes, I was just talking about this is very important, very interesting result here. What this result says. I just wanted to connect the NBTI with the soft error. Okay, what this relation says? This relation says that if if there is no stress, like if normally I am operating my circuit, in that case, let us assume if the soft error upset probability is approximately 50%, I'm assuming this is the roughly number. If the soft error upset probability is 50%, then if there is an impact of NBTI in the circuit, so threshold voltage is going to increase. In this case, the soft error upset probability will increase, because how it is possible? It is going to change the critical charge. Now, what is the critical charge? The critical charge is the minimum amount of charge it is stored at the sensitive node, that we can call it the critical charge. If high energy particle is striking at the sensitive node, and if the energy, if the charge of that high energy particle is more than the capability of your storage node, might be it can flip your logic. If it is less than that, it is perfectly fine. So the critical charge is one of the parameters that decides whether your circuit will flip the logic or not, and that depends what is the magnitude of your impulse that was generated due to this high energy particle strike. Okay, so if because the threshold voltage is high, the current will reduce. Current will reduce, it means the charge storage capacity or that will also reduce at the sensitive node. And if that will reduce the critical charge. And if critical charge is reducing, the impact of high energy particle will be more. Okay, so this is how it is related with. So ultimately, with the higher threshold voltage, critical charge will be less, and the soft error probability, upset probability will also be higher. Okay, so now here you can see the impact of NBTI is on negative side as well in this direction. Like if there is some aging effect in the chip and you are using it in the space, might be with the time your system may fail even though you have made it like a soft error resilient. So someone was asking like, can we mask it? I think who was discussing? He was discussing like, can we enclose through a material, something like that, hydrogen particles should not exist. So let us assume we have made it, but because of these changes, their susceptibility will be less than, and that can create a problem. Okay, so yeah, here is one simple relation, like at stress time 0, if you have some this critical charge, this will keep on reducing with the time. What it means, soft error upset probability will be higher. Okay, so this is what the relation is. Yeah.
Small down that, like I have little bit counterintuitive explanation.
Yeah, please.
Trip point of the inverter basically, it also depends on the threshold voltage of the PMOS as well as the NMOS. Now, if the threshold voltage of the PMOS and NMOS has increased because of the NBTI, then that means at the input, the pulse, which basically the pulse, the amplitude of the pulse has to be higher to flip the output voltage of the inverter.
No, if you see the trip point voltage, let me draw that VTC. I'm assuming it is a VDD. here I have something like VDD. Here is the trip point voltage. We call it the medium voltage. So here is the negative slope. Here is the negative slope, and here is the point where the threshold voltage of one of the transistor is, and here is the point where the threshold voltage of one of the transistor is. Okay. Now, if I change the threshold voltage, okay, if I change the threshold voltage, what is happening? Ultimately, if I have made my sizing in a such a way that the point at which the input and outputs are same, they are decided by the sizing of the transistor. Because if I will change the pull-up network, your waveform is going to be shift in this direction, okay? And if I am going to change the strength of pull-down network, your waveform is going to shift in this direction. So this is going to happen. This trip-point voltage, which we are deciding here, is decided by the sizing of the transistor. Let us assume I have fixed the sizing. If I have the fixed sizing, so ultimately your VM will be fixed. Now, the threshold voltage of the individual transistor will decide from where my slope will start. So let me draw one more VTC. I don't know how effective it is. Maybe someone can turn on your camera and you can focus it on the Zoom. They can see it. Okay. So let us assume I have one more VTC. Okay. Okay. And I'm assuming that this is the one of the VTH. Okay. This is one of the VTH. Now, changing the circuit, like if I have reduced the VTH, so your VTH will be somewhere here. It means that your waveform will be something like this one. Okay, so maybe the slope is not good. I can make it proper slope, 45 degree. Yeah. So your waveform will be something like this one. It will cross to the same point, and behavior will be something like this one. Okay, so here is the catch. Okay, so ultimately, if you are increase the threshold voltage, that will shift in the right direction, and that is what happens. Perfect. So, yeah. So the question is, if I want to understand the how I can analyze the effect of the soft error in combinatorial circuit. So let us see how it can be done. Okay. So let us assume I told you generally that impulse is modeled by the double exponential current, where we have a different rise time and the fall time. And if you have a different rise time and the fall time, and if you want to check it for the combinatorial circuit, this is the generally people used to do. Like what they do, they will apply one current pulse of different rise time and the fall time. Okay, and it is something like this one. And then they will see, like, because if I have an inverter, let us assume input was logic 1 and output was logic 0. Okay, so their magnitude is going to change because of this high energy particle. Okay, if the magnitude is going to change, output will start reducing, like input will start reducing, the output will start increasing. So they will touch at some point of time. So I will check at which point they are touching to each other, means V in is equal to V output. That time we can call them the critical charge. And if we integrate this current from 0 to T critical, that will be your critical charge. So to calculate simply, just integrate over the time from 0 to T critical, that will become the critical charge of your circuit. And that is, so let us assume one of the circuit that input becomes equal at this time, and for one circuit it becomes at this time, this will offer more critical charge. So this timing used to change for a same amplitude for different circuit, for different threshold voltage, and for different kind of characteristics. So if somehow we are able to, yeah, so this tolerance can also be improved by increasing the strength of transistor. If you are increasing the strength of transistor, definitely they will drive more current, and might be the current will be higher than that critical charge will be higher. So this is one of the way, like, yeah, these are some of the technique how you can improve the software robustness by changing the transistor sizing. But once it is fabricated, you have to consider different mechanism, because before fabrication that is perfectly fine, you can test them, but after fabrication that's a bit difficult. Okay, so this is how you test it, and simply I already told you, yeah, you have to inject a current pulse over here at the input of device under test, and then you have to observe the output, and accordingly you can check it out how it happens. Similarly, if you want to understand the impact of soft error in the sequential circuits like a memory, how you can do that. We know that in memory you have uh, uh, two storage nodes, typically for 60 SRAM cell. If I have a two storage node, then what I need to do? Simply, I will apply the similar kind of impulses. Okay, let me open the setup as well. So let us assume if I will apply, let us assume I have a Q and QB, these are the two storage nodes. What I will do, I will apply one current pulse over here. That depends like what logic I have stored there. If logic 0 is there, then I will apply direction of current will be decided like what kind of logic you have stored. I think I have already explained in the beginning of the slide. Okay, so the direction of current will be decided in such a way like what logic you have stored at Q and QB, and accordingly your other node will flip. So initially, let us assume my QB was 0, QB was 1, and Q was 0. So what will happen if I will keep on, if I will apply the current, charge will start accumulating at that node, and at some point they will cross and they will flip it, because that will cross the trip point of that circuit. Okay, because because it is a latch, right? So once it will cross the trip point, it will change the other inverter's logic and it cannot be recovered back then. Okay, so in the sequential circuit, like a memory, once it crosses the critical time or that point, it will flip the logic. So initially I was expecting my QB will be 1, Q is 0, but it's opposite. It becomes opposite after crossing that critical time. So this is the problem with the memory. So you have to come up with solutions how you can make your memory soft error resilient. There are many techniques, like dials is one of the technique. Maybe there are a lot of techniques like you can go through it. How to improve the critical charges. Okay, so this is doable. So this is how typically we used to test the soft error in the sequential circuits. So now if we see the soft error in combinational and sequential are a little bit different. In the sequential, the data used to flip. In combinational, it generates a glitch that can create one impulse. And if that impulse is controlling something, might be that can be triggered or that can be turned on, turned off, something like that. So that's also a problem. Let us assume I have passed, yeah, so the circuit which I was showing a chain of circuit. If that is that signal is used to turn on or turn off any devices, any module. So what will happen? If one impulse will pass to that circuit, it will turn on or turn off that device, which was not required. It should be remain same, but it will change its status. Okay, and that will become the complete failure of the system because of that small impulse at node. So we need to mask them. Proper masking scheme is really required. Okay, yeah.
What is the typical value of that peak time?
That depends which technology you are considering. Okay, so that is why I'm saying, like, I think he must have mentioned iron varies. So he must have mentioned like what should be the timing, what should be the amplitude. That depends on what parameter, like what charge particle you are considering. Because all charge particles have different energy and they have different kind of amplitude, different kind of timing, different kind of rise time and the fall time. You cannot fix the rise time and the fall time fixed for all technologies. It is technology dependent. So there is one relation how to decide the rise time and the fall time, and accordingly you can come up with that value and you can simulate it. So because this double exponential current you can create in the simulation setup, but what will the rise time, fall time, you should decide based on the technology, based on the other parameters as well, based on the charge particle which we are considering to test it. Okay. Any other questions? Okay. So, yes. Now let us talk about the challenges. What are the various challenges in the reliabilities? Okay. Reliability and security are very 180-degree out of phase, right? And I'm covering both the things. Huh? It means, single event transient, That is, yeah. So it depends. Like, see, yeah, very good question. Let us assume I have some memory having more than 2 storage nodes, because there are, if you see the recent radiation hardened memories, there are too many storage nodes, but other than this, there are other secondary nodes which can decide the logic. So if high energy particle is striking at more than 2, that can be the dual upset or multiple upset. There is also possible. So we need to make, like 60 is having only one sensitive node, so the single event upset will happen here. But if you are talking about radiation hardened memory, like where we have more than 2 storage nodes, I can show, like you can just search RSBD, you can find that memory. So there are more than 2 storage nodes. So if the strike is happening at 2 nodes, might be it can flip the logic. So they are also reducing the probability of upset by increasing the sensitive node, so that if high energy particle is striking at one node, might be other circuitry is helping to recover that back. So this is what is happening. Okay, but if the strike is happening on both the nodes, then it will fail. So this will ultimately reduce the upset probability, but of course there is always a chance of the upset. Okay, so as per the latest, not latest because this is the old slide, but yes, I would call it latest only, because some of the projection which was expected to finish is still not finished. So I would say it is also. So there are 2 kind of reliability concerns based on the prediction time, that is the near-term reliability issues and the long-term. Near-term, it is 22, but still some of the concerns are not resolved. So you can say it is also the near-term problem. Okay, it's not the past problem, it's still the current problem. And there are some long-term reliability issues. So let us try to understand what these 2 reliability issues are. Okay, so if you talk about the near-term reliability issues, consider this is 25 now. Okay, fine, it will work. Okay, so if you think of like near-term reliability issues, definitely time-dependent, like temporal degradations like TDDB, NBTI, PBTI, SCI, all these are the concern. Okay, and not only the planar devices, but in non-planar devices, because nowadays we are moving towards the other kind of devices like cylindrical gate all around and all this kind of tunnel fate and all those things. So they are non-planar kind of devices. So understanding the NBTI, properly model them like SCI is equally important, because we are going to use those kind of devices in near future. So we need to understand what is the impact of this kind of temporal degradations in the non-planar devices, not only in the planar devices, because planar devices are the older technologies now, because now we are going to use the newer ones. So we need to understand what is the impact of all these kind of variabilities in the non-planar devices. So this is one of the challenge, one of the concern that we need to take care of. Gate to contact breakdown is also very important, because we keep on reducing the size, so there is a possibility of breaking down, like whether we are able to properly connect the gate terminal with the polysilicon and all those things, metal layers or not. If that contact is not good, might be it can break and it can fail the systems. So that's also one of the reliability concern. The third is like yeah, of course, increasing statistical variation of intrinsic failure mechanism is skill in non-planar devices. This is already told. I have already told you. 3 interconnect reliability challenges, because now we are talking about 3D IC and all those things. So the reliability of those things are equally important, because before we send it into the market, definitely we need to test the reliability of those things as well. So that's really very important. Okay. And the reduced reliability margin drive understanding at the circuit level. So as of now, all these models like NBTI, PBTI, SCI, all these models are developed with respect to the single devices only. But how this device will help, like how this device reliability concern will help in understanding the circuit at the circuit level, this is also equally important. Okay, because of course you can test. Yeah, so for that, Mozra model is one of the well-known model, which we call it the MOSFET reliability and analysis model. In the ASUSPICE tool, you can find it, where you can test the reliability. You can test the NBTI, PBTI, SCI, and TDDB effects. Okay, but the proper testing at the circuit level is really very important, because I think there was one abstraction graph, last slide of the last lecture, where I showed a kind of V shape, where the effect of NBTI was in the material level, but their impact at the different abstraction level was different. Okay, so understanding those impact at the different abstraction level from circuit to system to modules, that need to be investigated, that need to be analyzed. Okay, so these are the near-term reliability issues, and of course they are very serious, especially if I am going to use these kind of things on critical applications like medical devices, aerospace, space applications, defense applications. They are very, very sensitive domain where we need to maintain the reliability. Otherwise, what will happen? If let us assume I have some equipment near to the patient and some X-rays, I turn on the X-ray, might be something can generate a glitch and everything can go, right? So that's seriousness is, and we need to take care of all these things as well, especially on the mission applications. So these are some near-term reliability issues. Some long-term reliability issues, especially for the device guys who are interested in this domain. For them, some of the long-term reliability issues are like how we can come up with the new novel material that can tolerate those things. There is a less effect of NBTIs and all those things. This is one of the scope where you can think of. Novel device structure, you can think of like how we can mitigate the impact of NBTI, and all those things at the new device structure. That's also one of the possibility. How you can change, like changing the dielectric material, changing the material type, high K, low K, whatever you can do. That's one of the possibility. So yeah, so understanding and controlling the failure mechanism at the new material level, at the level of transistor, interconnect, material. So all these things you can think of like how I can avoid this failure. So this is one of the scope where people can think of at the device level and the material level, at the interconnects as well, because the interconnect is also equally important, not only the devices, but because we are connecting two devices through the wires, through the interconnects. So if they are not reliable enough, even though you have made reliable devices, that is not going to work properly. So interconnect reliability is equally important than the device reliability or circuit reliability. Yes, and the shifting, I think I have already told you, the shifting from the device to system level reliability understanding is equally important because their impact is different. Even though the origin is same at the device level, but at the system level, their impact is a bit different. So how you can predict those failure, like timing violation, system failure, and how you can relate that timing violation with the NBTI is equally important. So that's also important to understand. And muon-induced soft error rate, yeah, this is a different kind of particle that can impact at the lower technologies. So with this one, that's end of the reliability. Thank you so much. So if you have any questions, yeah, still we have some time. I can take up some questions on reliability and security both, on both the directions. And I am in between here. Okay, you can ask the questions.